when the SIAM list came out of like the top 10 coolest algorithms or something, I was sad to see that the Kalman filter wasn't on there because I'm a controls guy. But I was happy that my proposal to present the Kalman filter went over well with Derek and the rest of the SIAM folks. So anyway, yeah, so my name is Justin Pearson. I'm a third-year ECE grad student here at UCSB, and I'm going to tell you about the Kalman filter. The Kalman filter is just kind of this combination, like the basic stripped down Kalman filter is just the combination of two ideas, this linear systems as a way of modeling physical processes, and this efficient algorithm called linear recursive estimation. And so those two things together comprise the Kalman filter, and so that's what we'll be talking about. So first, just to give sort of a bird's eye view, the Kalman filter is an efficient algorithm for estimating the state of a system from noisy measurements. And so almost every adjective has a more rigorous mathematical definition. But at just sort of the top level, the idea is as follows. We have some sort of dynamical system here, like a rocket, whose movement is governed by like F equals ma type dynamics. There are some inputs, like fins and thrusters, that can tell where the rocket's going to go. And we have instrumented the rocket with a bunch of sensors, like accelerometers and gyroscopes. There's some desired trajectory that we would like the rocket to follow. And there's a whole lot of other bad trajectories that we'd like the rocket to not follow. And I chose a rocket here because the Kalman filter got popular in the 60s when NASA was trying to get a man on the moon. And Rudolf Kalman was visiting NASA Ames up in the San Francisco Bay Area. And he realized that this method that he had this algorithm that he had been developing, would be well suited for estimating trajectories, for computing trajectories of spacecraft. And so it was that was what made the Kalman filter catch on and become eventually a very famous and general algorithm. Okay, so that's the high level idea. The big question, especially in control theory where I'm from, is given that you know the system itself and you've instrumented it with some measurements that will tell you things about how the system is evolving, how can you choose your input based on your measurements and the physics, your knowledge of the system itself, in order to make the trajectory do what you want it to do? Okay, so let's focus first on this big long sentence on just what is a system. And so let's talk about linear systems. So a discrete time, linear time-invariant dynamical system is just a set of matrix equations of this form. So there's some constant real A, B, C, D matrices, and there's a sequence of vectors x, y, and u that evolve according to this equation here. It's called discrete time because these equations evolve over the natural numbers and not the real numbers. They're linear because the right-hand sides are linear in x and u. They're time invariant because a, b, c, d are not functions of I. They're just fixed known matrices. And these equations specify this vector recursion in x. The whole idea is that if you're given some initial condition and some sequence of inputs u, you could calculate the sequence of states and the sequence of outputs y. Okay, and the big question that in control theory that we spend a lot of time thinking about is, if I only get to observe the outputs y, can I cook up some rule for u, for the inputs, in order to make the sequence of states x good in some way? And in linear systems, what good means most of the time is, can you drive x, the state, to 0, the 0 vector? If you can drive it to 0, then, hand waving, because it's a linear system, then you can reason that you can drive it kind of anywhere else you want to go. And so, so often driving the state to 0 is the thing that control theorists want to think about. So this is an example of a linear system from a class that I had the good fortune to take that shows, I think, some of the power of linear systems. I think has got me really excited about them. The idea is, here is a continuous time, linear time invariant system with some A, B, and C matrices that we know. This is a model for a positioning table, like on a microscope. There's a computer-controlled 3D printer or something. The position of the table has some coordinates, some x and y, and there are motor torques that move the table around, these two inputs u, and there's 16 states of the system that are sort of under the hood, governing the evolution of those of the table. So the problem is, if you have some desired position that you want the table to be at, what sequence of motor torques should you apply in order to make the position of the table go there? So the simple approach would be just to say, okay, well, at steady state, what motor torques will I have to be applying in order for x dot to be 0? And so if you set x dot equal to 0 and set x, say y has to be the desired y value, and you solve for u, you get minus 0.63 and 0.36. Just these are the steady state values. And if you just plug those in as your input, so here's u1 and u2, if you have u go to minus 0.63 and 0.36, then over time, the output, y1 and y2, will wiggle around for a long time and eventually get to the desired 1 and minus 0.2, sorry, and minus 2. But this takes a long time. It takes 1,500 seconds for y to sort of settle down. However, if you use some very clever input waveforms, then you can do it a lot faster. So here, u1 and u2, they don't start out at going to their steady state values, but they wiggle around a lot first in a very clever way, and then eventually snap down to minus 0.63 and 0.36 as their steady state values. And you can see the outputs wiggle around in a very curious way and eventually end up at 1 and minus 2. But this only takes 50 seconds. And so here, we've chosen a very clever input in order to make y get to where we want it to go really quickly, faster than 1,500 seconds in the previous example. So this kind of example is what got me really excited about linear systems, because it allows you to be clever in some ways that have some neat physical effects. Okay. So what we just showed was sort of a hand wavy, it's possible to pick an input that has this effect. But let's talk about the actual controllers that might do that in practice. And so a common class of controllers are called state feedback controllers. The idea is if you have some discrete linear time invariant system, and D is 0 and C is just the identity matrix, then what this is saying is that you can observe all of the states directly. There's no mixing or no subspace that you're limited to. And so with that, reading the state directly, in principle, you could pick a control law that's just Kx. And this has sort of intuitive appeal because the idea is if you're trying to drive the state to 0, well, if the state's far away from 0, then maybe you should apply a big input, and if the state is close to 0, you should maybe apply a small input. So that's sort of the intuition behind why this control law might make sense. And if you plug this control law in, then the entire system will just evolve like this, like some matrix to some power. And we as control engineers really like A-B pairs such that there exists a K so that you can make this matrix go to 0 in a timely fashion. And there's a whole lot of nice theory around what are called controllable pairs. So what this looks like in sort of a block diagram form is you have this system here, where here I've made C the identity and D is just 0. What comes out is what you measure Y. This goes into this block, the controller, which then computes Kx, and the input goes back into the system. And so this block is called the state feedback controller, and this is called the state feedback control thing because the output is just the state. And this is just a graphical way of looking at a handful of equations in a dynamical system. Okay, so often you don't get the entire state to look at. You're actually stuck with Cx plus du or something. And so the question is, what should you do then? Well, one idea would be, let's just keep the same controller before. Maybe you put a lot of time into trying to figure out what this K should be. And instead, whatever this output is, you'll just feed it into some block called an estimator. From this estimator, which will cook up an estimate of the state x hat, feed it into the controller. And then instead of Kx, you'll just compute Kx hat and feed that into the system. And so the whole idea is, if you don't have the state, maybe you can cook it, you can estimate it, and then use that estimate with the same state feedback controller from before. And one of the big takeaways from a linear control systems class is that there's in a hand wavy sense, there's a separation theorem that says, hey, you can design a controller, a state feedback control law, and an estimator separately, and then when you combine them, it actually won't be too bad. It can still be a good controller, even if you design this, assuming that you had the state and you really don't. So one idea. So now we're going to focus on this block here. What should we do with this estimator? One idea is you could just pick your best guess that you had for the initial state and then propagate it forward in time as the system evolves. And if you happen to pick x hat 0 to be exactly the initial condition of the system itself, then it would just evolve and estimated state would be the exact real state and life would be good. But there's a couple of downsides to this. One is that it ignores the measurements. There's absolutely no dependence on the measurements here. So you're just sort of closing your eyes and shutting your ears and propagating your guess forward with time. The other criticism is that this whole system as a whole doesn't account for any sort of disturbances or measurement noises that might be corrupting that might be pushing around your system or corrupting the noise in your measurements. And so, for example, if this is an airplane whose dynamics are like this would be like wind. The disturbance would be wind pushing the state around, and there would be some sort of noise on the measurements, like due to electronics or something. So the idea is that this just propagating your guess forward is kind of nice if you did a good job of guessing it, but it of course has this downside of not using the measurements. So instead, let's blow this up again, and this is the realm where the Kalman filter applies. We have a discrete time, linear time invariant system that is being pushed around by these random variables w and v, and the output goes into this estimator block, and this is where the Kalman filter comes in. It maintains a state estimate for what the state x is, and then every time a measurement comes in, it updates that measurement according to some rule that we're going to talk about now. So when we say that yes?
Random variables?
Sure. Yeah, each of these, and I'm sorry, I did tune this talk to not go too far into the random variable parts, but each of these are random variables with some like finite mean and distribution with known covariance. Yeah. So when we say that the Kalman filter is estimating the state of a system, this is what we're talking about. There's some system that is being, some linear system that's being pushed around a little bit by noise, and we have this block here that is going to try to estimate its state. Next, we need to talk about what do we mean when we say that it's efficient and it's an efficient estimator. So this is the second part of the talk where we're going to talk about an algorithm called linear recursive estimation. Here's the problem setup. So the linear recursive estimator just estimates a constant vector based on a sequence of noisy measurements. And so there's some constant vector x. Let's get the things up. There's some unknown constant vector x. We measure a sequence of measurements y that are linear functions of the unknown constant x that have been corrupted by zero mean measurement noise. And we're trying to figure out what this unknown constant is. So the example is that I have some big scale here that's like a freight scale, and so it can't measure any one person's weight very well. But so maybe if we're trying to figure out everybody's weight in the room, maybe I can take people up in groups, and everybody will stand on the scale, and we'll write down what the scale says, and then we'll bring up a new group of people and mix the people around. And the idea is what the scale will measure at every time step is some linear combination of the people. So in this case, the scale thing, this C matrix would just be ones. It would be a row vector that's as long as there are people in the room, and it'll be ones and zeros. There'll be a 1 if the person is standing on the scale, and a 0 if not. And if we do this over and over again with different mixtures of people, the idea is it would be nice if we could combine these measurements and this knowledge of who was standing on the scale at which experiment in order to estimate the weight of the people in the room.
It's not time dependent.
Yes. So in this case, exactly right. Each of these, I'm glad you brought this up. In the linear dynamical systems case, this matrix is just a constant time invariant matrix that is the same over with each time step. But for the linear recursive estimator, this matrix is allowed to change at each time step. Yeah, I'm glad you brought that up. So the scale thing is just an example where we have some unknown constant that is fixed. Unlike a linear system, it's not evolving with time. But the experiment, this C matrix, essentially captures what's going on with each experiment. And that is allowed to change from experiment to experiment. OK, and so how can we try to estimate this unknown constant given this sequence of measurements. So what's known here is we know how each experiment is built, so we know all the CIs. We know the covariance of the random variable. And of course, we are receiving all these measurements, so the sequence of measurements is known. Let's call x hat of I our estimate of x after I measurements. And the whole idea of the linear recursive estimator is given that some new measurement we will update our estimate from whatever it was before to some new estimate. But you're not allowed to store all of the previous all of the previous measurements or any of the previous estimates. You're only allowed to keep sort of a running estimate that time you get a measurement. This is why the linear recursive estimator is called recursive, because the new one depends on the old estimate, and it's efficient because you don't have to allocate all the memory to store all these previous measurements. Okay, so here's the rule for the linear recursive estimator. The update equation is just a blend of the previous estimate in blue here and what's called the innovations, this thing here. And so there's some matrix K. So the whole idea is your new estimate should be whatever it was before plus some function of how wrong was the measurement that you would predict. So you measured yi, but you were expecting to and then times your estimate. So if this were correct, if your estimate, if your state estimate is correct, then CI this thing would be exactly what you would measure. If this is different than measure, then there's some sort of error. This is like the measurement error between what you did measure and what you expected to measure, and that should be allowed to tweak your estimate of the state. And so this is the whole idea of the linear recursive estimator is your estimate should be updated according to how wrong it predicted the measurement. So the whole idea now is let's pick K, this what's called the estimator gain, to minimize the mean square error of the estimate. So just a quick note, this x hat of I depends on y, and y depends on this random variable v. And so y is a random variable. And so x hat is a random variable, and so the square of the distance from x is also a random variable, and you can take its expectation. And so this is so that's how to interpret this expression: is this thing is a random variable, and you're taking its expectation. Okay, this is to find the k that minimizes the mean square error is just this three-step process. Let E be the estimation error, and you can write x hat of I according to the measurement update equation here that we were just looking at on the previous screen. Each measurement is just this. This is the measurement equation, and so you plug that in, and now you rearrange some stuff, and you get you can have E of I minus 1. And so we've expressed the estimation error, the ith step, as a function of the estimation error on the previous step, and there's some noise. Step 2 is just take the covariance of both sides of this function. So the vi is a random variable, e depends on x hat is a random variable, and so you can take, so this is equality in random variables. You can take the covariance of both sides. This is what's going on behind the scenes here. If you have two independent random variables, you can take their covariance, and the covariance of the sum of some weighted sum of them is essentially some sort of weird symmetric weighted sum of the covariances of the individual random variables. And so taking cov of both sides yields this equation, where this is essentially your like m, and this k is your n. Please.
Are primes transpose?
Yes, I'm sorry, that's exactly right. Yep, transpose. You got it. Yep. So that was step 2. Is we express the error sort of recursively, and the covariance of the error. This is essentially how uncertain you are in the quality of your estimate. So, and you can express this recursively. The last step is to massage this mean square error. So this is E transpose, which you can swap around. It's the same as trace of E transpose. Operators and the covariance of Doing a little hand waving here, it turns out that E is zero mean, and so that's how you get from here to here. And P is just the covariance of E. So the whole idea is that you are trying to find K to minimize this expectation, and this expectation is just the trace of this matrix. So in order to find K to minimize this, you take the derivative of this with respect to the matrix K, set it equal to 0, and solve for K. So this is just sort of an expedited hand-wavy explanation of how you find K. So if you do this, what you get is K equals this big long thing. So I mean, that's pretty much taking the derivative of this expression with respect to K and solving for, and setting it equal to 0 and solving for K. This matrix inverse here, you might worry about whether or not it exists. And the way that I think about this is, well, this is a covariance matrix. This is the covariance of the noise, so it's positive definite. This P is the covariance of the estimation error, so it's positive definite. And this looks like C squared. So these all look like positive numbers in here. And so I don't lose sleep about worrying about whether or not the inverse exists. Okay. So that was how you find the form of the optimal estimator in terms of minimizing the mean square error. So the whole algorithm boils down to this. Remember your estimate of the constant and how uncertain you are in that estimate. Every time a new measurement comes in, compute the estimator gain K, and then update your estimate and the covariance. So every time a measurement comes in, compute the K. This is the equation from the previous slide. Update it with this measurement, with this update equation, and then update, this is the covariance equation that is expressed recursively. This looks ugly, but actually when you apply it to a linear system where the C matrix is constant, it actually boils, all of the I subscripts go away. So here's a method in a class for a linear recursive estimator. And all you do, the measurement update method takes, this is like self, for, well, it takes the measurement, it pulls out a bunch of the members of the class, and then just applies these equations that are exactly these, only without all the ugly subscripts. So let's see an example. Here's an example that is also from that class that I like about linear systems, where it's a kind of a tomography example. So the idea is that there's an airplane that is flying over the Earth, and we're trying to look for oil or minerals or something, and it has this little like laser radar thing that is shooting a beam into the Earth. And the measurement that comes back from this beam is related to all of the cells. So each cell is like a chunk of Earth that has some density. We assume the density is constant in that cell, and we're trying to figure out what is the density of all these cells. And the high density ones will be the minerals that we're interested in or whatever. And so the idea is by flying the airplane around and shooting different beams down, can we figure out what is the density of all of the cells if we only get sort of the line integral for each over all of the cells for each line? In other words,
sorry, is this like underground?
Yeah, I'm sorry. The idea is I should have drawn like a ground line here or something. Exactly. Yeah, no, this is an office building. Yeah, so the idea is here's ground level, and the airplane is shooting this laser down. And so what the airplane would read, it's one scalar measurement that it would read from this laser is this distance L7 times the density X7 plus this distance L4 times the density X4 plus this distance L5 times the density X5. The idea is it's the line integral of this line with all of the densities. Okay, and so we have an equation that looks like this. So the ith laser beam, the measurement that you read from that experiment is a weighted sum of all of the densities, where this big old row vector thing is essentially going to be, it's going to be 0 if the line never even goes through that cell, and it'll be the length of the line through that cell otherwise, plus there's some noise. The noise here, the idea is the length that the laser has to go through all this hazy, this is like in LA or something, the length that the laser has to go through this haze is related to how noisy the measurement is. And so all of these covariances are assumed to be known because we know where the airplane is and how high it is over the ground. So this is exactly the form that we need to apply the linear recursive estimator. So here's what happens. After the first line goes through, so initially we have no idea of what's, so this is the 30 by 30 grid cells under the Earth, and we're going to do like 1,200 lines, 1,200 lasers shoot into the ground. Initially we have no idea what is under the ground, so it's all just a uniform density. After the first laser shoots in and we apply this update equation, all of the pixels update due to this knowledge, not just the ones that get hit by the line. After the second one, another line goes through. These ones also changed a little bit, and so on. If you repeat this process over and over again, every line updates the knowledge of what the densities are. And so if you just play this on fast, well, so that's what happens. This is, yeah, so that's what happens. This is not surprisingly the true density, and so it works. Of course, I wouldn't put it in if it didn't work. Another thing that you might be thinking is, well, Justin, you have a sequence of scalar measurements that you are making with a constant vector, and they're all linear. So why didn't you just line them all up in a big matrix equation and then you have a least squares problem? And then you would get this answer, which looks similar. In other words, why didn't you just do this? You have capital N measurements. Each measurement has some linear relationship with this bunch of pixels whose density you're trying to estimate, and each one has some noise associated with it. So why didn't you just do like the pseudo-inverse of it? There's a couple of reasons. The first one is it could be a large matrix pseudo-inverse. If you were like doing this all day long, you could have zillions and zillions of measurements, and then this would be a big matrix. In practice, this is not really a problem because there's an algorithm for least squares that allows you to do sort of a rank 1 update, sort of like the linear recursive estimator, where you adjust, where you can recursively build up a least squares solution from a big long sequence of measurements. And so this is not a big problem for least squares. Another criticism might be, well, in least squares, you're just ignoring the noise here. In a sense, what that means is you're assuming that it is all sort of small and equally uncertain. What if it's not equally uncertain? Sometimes the airplane might have been very high up, it might have been a lot of haze, and that would be a big covariance, or it might be very small, it might be very close to the ground, and there would be a little covariance. And in practice, this is not a big problem because of an extension of least squares called weighted least squares, where you can weight certain measurements, essentially varying levels of uncertainty, and that will make really noisy measurements be not count for as much in the solution. There's one more point, which is that least squares, because it ignores this noise, it assumes that essentially all the noise is uncorrelated. And because of that, least squares doesn't really leverage the relationships that there might be between successive measurements. And this is something where the linear recursive estimator can help you out, but least squares, because it just ignores the noise, is not quite an appropriate. It's a very useful sledgehammer, but in this case, it's not quite as appropriate. So here's what I mean by correlated noise. So suppose instead that the airplane, as it's flying overhead, instead of just having a single laser beam that shoots down, it actually has two of them that are fixed, by this armature. And so every measurement is, every measurement is two laser beams shooting down. So this looks like this. Every measurement, there are two scalars that you read that are linear combinations of the state, and then there's some noise. And the thing is, because these two laser beams are fixed at this fixed angle, as it's flying around, it's like shooting these laser beams down. And if this covariance is very small because it's close to the ground or it's pointing directly down, then you can say something about how bad you would expect the other noise to be because of your knowledge of how they're linked together. And so, in other words, the covariance matrix for these two noises would have non-zero elements at the off-diagonal, indicating that you do have some information about how the two noise terms are related. And in least squares, you would just throw this away. You would say, oh, well, it's small, and they're all about the same. But the linear recursive estimator allows have problems, analyze problems where in a single measurement, in a single experiment, the noise that you're suffering from is correlated. Okay. So in conclusion, for this part, the linear recursive estimator is just an algorithm for estimating a constant vector here from a sequence of noisy measurements. And this is sort of the bread and butter. And that's it for the linear recursive estimator. So the Kalman filter is just a combination of those two ideas. The Kalman filter applies the linear recursive estimator to a discrete time linear system. So this is what we were just looking at. We have a discrete time linear system that's driven by, that's being hit with some noise. And we have this estimator that will propagate, sort of time update its estimate forward in time. And every time it gets a measurement, it will update its estimate some. And here is how it updates the measurement. Initially, so this is the Kalman filter. The Kalman filter initializes its state estimate to be the best guess that it has for the initial condition, and its best idea of what that uncertainty is in that guess. And then every time step of the system, it propagates its guess forward in time according to the dynamics, assuming that there is no noise. Because the noise is zero mean, this is kind of the most reasonable, best assumption that it can make about how to propagate its estimate forward in time. The covariance, the uncertainty of the estimate, is also propagated forward in time. And this equation comes from this. So the estimation error in the discrete time system evolves like this. So so evolves like this, where Qi is the covariance of Wi. This is also assumed known. And again, this is just using the same rule as before. If you take the covariance of both sides of this, you get this equation. When a measurement comes in, the Kalman filter applies a measurement update in the exact same way that the linear recursive estimator would, except it's even a little bit easier because the C matrix for the discrete time system is time invariant. The C matrix doesn't even change. And so when a measurement comes in, the Kalman filter computes this K matrix, uses the K matrix to update its estimate of the state, and then uses the K matrix to update its uncertainty. So that's the Kalman filter. And I want to say a couple of things about it, and I have a nice example, and then we're done. The code for the Kalman filter is real short. This is just the code that we saw before from the linear recursive estimator. And this is just the code, this is the method, time update method that takes as an input whatever the input of the system that you applied was, and propagates the state forward according to the dynamics, and the covariance forward according to also to the dynamics. So these equations are just here. These equations are just here, and they're the same as linear recursive estimator. So I have some class Kalman filter. It has two methods. And it has also, as the constructor for that class takes, essentially the dynamics of the system and the covariance of the noises. So it doesn't look too bad when you actually have it in the code. There's one more thing that I want to say about the Kalman filter, and that is these measurement updates. So the measurement updates don't have to happen synchronously with the time updates. Here's the idea. The linear dynamical system, the way that it is constructed is the state evolves, and at every time step, the state evolves a little bit, and you get an output, some y. And in a real system, you could have the system evolving in accordance with some linear system, but the measurements don't necessarily come in every time step. So an example would be, you maybe have a little airplane that is flying around that has a GPS antenna on it. And the dynamics of that airplane, the autopilot propagates forward at 100 hertz. So the autopilot is trying to stabilize this airplane, and it's running a Kalman filter, and it's propagating its estimate of where the position of the plane is and its orientation forward at 100 hertz. But only every 1 hertz does a GPS update come in that the plane can use to correct that estimate. And so in that case, there's absolutely no reason why, when that measurement comes in, the plane can compute the estimator gain, compute the measurement, the estimate update, and compute the covariance update. it can do that with the evolution of the system. And so it turned out to be really handy when I worked on some airplanes at a company before coming to grad school. We had these little hand-launched remote-controlled drones that the Army was using for reconnaissance, and they were running an autopilot on there that was updating its estimate of the state at 100 hertz, and it had, you know, a 10 hertz magnetometer and a 1 hertz GPS and a 50 hertz accelerometer, and all of those things could be updated sort of on an asynchronous ad hoc basis according to these equations that were totally decoupled from the evolution of the propagation of the state in the first place. Okay, so you've been very patient. Oh, sorry, there's one more thing before I get to the cool demo. These are two things that you would need to know if you were going to talk about Kalman filters at a cocktail party. Because people talk about, something that I haven't mentioned is I'm hoping my Kalman filter experts will you know, tell me if I get it wrong. But this is my understanding of how it works. Over all linear filters, all filters that take a sequence of measurements as an input, and then as a linear function of those measurements produce a sequence of state estimates, the Kalman filter is the one that minimizes the mean square error of those estimates. And this is essentially a consequence of, so this is when people say the Kalman filter is optimal, they mean these two things. And this thing is a consequence of essentially the recursive estimator. We pick K specifically to minimize the mean square error of the uncertainty. This thing is saying that if the noise, if the W and the V are Gaussian random variables, so you know their zero mean and their covariance, and you also know that their distributions are Gaussian, the Kalman filter minimizes the mean square error over all filters, even the nonlinear ones. And the idea here is that if the noises are Gaussian, then, and you run those Gaussians through this linear system, then the state and the measurement will also be Gaussian, and they'll be jointly Gaussian, and the state conditioned, and this is very hand-wavy, so I'm just telling you what you would need to say at a cocktail party. So the state conditioned on all of the previous measurements. This is a conditional on a joint Gaussian, also Gaussian, and the Kalman filter happens to pick the mean of that Gaussian as its estimate, which also minimizes the mean square error. So that's, I just felt like I was compelled to put, please. I'm sorry?
Kalman filter is for sure not optimal.
Perfect.
You're minimizing an error that is usually defined. So when you speak about optimal, you're meaning about performance, about time, about fuel, all that. So this doesn't minimize any kind of like that. So that's why people are working on other particle filters and stuff to somehow include optimizing the Kalman filter.
Victor, yeah.
Yeah, so you think it really is optimal over all Gaussian? The thing is, you use the particle filter, if you have a non-Gaussian distribution, so it can represent a different distribution. If you have a particle filter, you can represent any distribution you want, right? So you can guarantee optimality. But if you have a Gaussian noise, you can guarantee that the Kalman filter will be optimal for any MSC.
Yeah,
if you have
so,
a linear system.
Yeah, optimality in the MSC is kind of a back statement because you're minimizing an error that it doesn't optimize something in general. You're minimizing an error. So when we talk about optimality, you have an optimization. So this is not usually defined. You don't claim optimality on that.
No, it's optimal over, it's the best estimator you can have. It's optimal in the sense of it's physically optimal.
You can go
It's
ahead.
a definition problem. It's the best linear unbiased estimator. What he's saying is if you're designing an optimization, you can set whatever criteria you want.
Exactly, yeah.
And that's different. So if your criteria is mean squared error only, then
Okay, yeah. Now you're right.
but in the literature this would be the
Yeah.
blue
Yeah.
linear unbiased. That's linear unbiased estimator.
So if you were going to a cocktail party with these people from my lab, you will have to be extremely careful. And I'm thankful that they're here in order to correct, you know, to point these things out. But I think for a random, uniformly sampled in Isla Vista cocktail party, this would be sufficient. But thanks, Kyriakos. Yeah, I appreciate it, guys. Yeah. Okay.
And also, I think in the previous slide, that's just a note. Maybe you didn't say it, but so the K people that just know it as a Kalman game, so that's for the people that they're not familiar with control. So A is the Kalman game. So P is just, you can call it like a reconstruction or the variance metric. So yeah, so the famous Kalman filter was actually this K, this Kalman game.
Cool. Yeah, I mean, but it's a good note. You might say, why is this K here? And it's confusing because the state feedback gain, the typical notation that I'm familiar with, is also U equals KX. And so that's kind of a collision of notations. Anyway, but yeah, I consider this to have sort of precedence because of Kalman. Okay. Great. Okay. Well, so here is an application where the Kalman filter might come in useful. So I don't know, when I saw that, it just screamed Kalman filter to me. So I stood up in the theater. Okay, so this was in the artist's conception for the scene, I think. There's a man who's falling off a building, and there's this cushion on the ground, and he has some position, and this is no longer the state and measurement because we're being a little bit slow. That was Mission Impossible 4.
Oh, okay.
Came out in 2009 or something. And he has some velocity, some u and v. So these are all scalars, and he's flying through the air. The cushion, we're saying, can use some sort of, I don't know, LiDAR scanning thing in order to read his position, which is this blue dot. But it doesn't measure his velocity. It just gets those two dots, and it just gets his position. And you can probably imagine that there's maybe a difference in the noise that it measures. It probably can tell this direction pretty well, but depth maybe not so well. So you could have different covariances in those two directions. And based on that sequence of measurements that it gets as the guy is falling through the air, the Kalman filter will produce an estimate of what his position is and what his velocity is. And there will be an uncertainty associated with both of those things, which is why here's the uncertainty of the position, and here's this fuzzy arrow because it's uncertainty in his velocity. And the Kalman filter's only job is to report that state to some sort of controller. And that controller, given that position and that velocity, can calculate where you would expect the guy to land based on that position and velocity. And so the controller would then use this point here as the set point for supposing that this cushion had the ability to kind of push itself around a little bit, because otherwise it wouldn't be a very good cushion. You'd have to be very precise. So assuming the cushion can kind of push itself around, the cushion would then try to move itself to the target point that the guy would land on. So here's a MATLAB simulation of that scene that I've made for you. So the idea is, this is the big picture. This is a zoom in of that picture. The guy is here on the building, and the initial state of the Kalman filter, it kind of doesn't matter, but initially, we'll just say, oh, maybe all buildings are 100 meters tall or something, and there's some uncertainty with that estimate. And we suppose that that the initial velocity is 0. And so, let's see, it's hard to see, but there is a small pink line down to the projected landing position here. And this is just his trajectory if he were here with the velocity. Okay, so as the system evolves, he's flying through the air, but we're saying that the cushion doesn't get a measurement every instance, every time step. He only gets it every 10 time steps or something. So the guy flies through the air. This position can't update because it can't do a measurement update because he has no measurements. Eventually a measurement comes in. So here's the measurement, here's the zoom in. When a measurement comes in, the Kalman filter updates its estimate to a new estimate that is kind of between the original one and what the measurement is. And it's not exactly on the line because there's also the velocity, which is also part of the state that you're not seeing here. And the uncertainty in the estimate has now shrunk a little bit because of the information from the estimate. And now you can see the pink line a little bit easier. This is how the guy would go if this were his exact position and velocity. And so this thing here would be the set point of the cushion as the cushion is deciding where to try to go to catch him. And so as you propagate the system a little bit more, eventually, so another thing to note here is that the estimation covariance is growing over time because the system knows that the man is being pushed around. There's a disturbance that is pushing the guy's state around, and the longer you wait and don't get a measurement, the more that your uncertainty will grow. And so eventually you get another measurement. The estimate now moves from whatever it was before to kind of closer to the measurement, and the estimation error shrinks a little bit. And so as you play this, as it grows over time, a new measurement comes in, and so we'll just play it. Wham. And this, luckily, I mean, I only made the pad like 1 meter wide. It really was kind of too small.
Fired like a movie.
Yes. Yeah, that would have been cool. Choo-choo. Yeah. So I guess just a couple of things to note here is that initially the covariance, the quality, the uncertainty in the estimate is quite large, and with each additional measurement, it gets smaller. But it never gets all the way to 0, and it won't get all the way to 0 in a hand-wavy sense because the estimator will know that there's always some measurement error and there's always some disturbance pushing around the state. And so it can never, the state is constantly moving and jiggling around, and so it kind of can't zoom in perfectly on the state. Yeah, and I think that's pretty much it. Yeah, so anyway, just to see it one more time, it's kind of fun. I don't know, it's kind of fun, and I put a lot of time into it. So we're going to watch it again. Yeah, so you can see that every time there's a new measurement, the state jumps a little bit between that and the previous one. Okay. Yeah, thanks very much. Yeah.